right. Okay, so the first talk after the break is Luca Cipelletti, who's already set up. So he's going to talk about time length scale superposition in glassy suspensions of ultra-low cross-link microgels. Welcome, Luca. I'm not sure if we've seen you here in Bangalore before, so welcome to...
Not yet, but I'm very happy to be here, and thanks a lot to the organizer for inviting me, and good morning to everybody. So I will present our work on these ultra-low cross-linked microgels. This is mainly the work of two postdocs, in Alessandro Martinelli, who's still in Montpellier, Raman, who was in Montpellier, now she moved to Strasbourg. And it has been done in collaboration with the group of Andrea Scotti and his postdoc Alexander Petronin, and by my colleague Domenico and myself. So let me start with some motivation for this work. I suppose that this slide is not really necessary here. I would just like to make the point here that colloidal systems have been studied a lot in order to understand things about the glass transition. And in the past years, people have started working essentially on colloidal hard spheres. And this is what a colloidal hard sphere would look like under the microscope. And it has been established that colloidal hard spheres are fragile glass formers. People have measured over several decades the increase of the relaxation time, the structural relaxation time, as a function of the control parameter in this system, which is the volume fraction occupied by the particles. And it follows VFT-like increase on approaching the colloidal glass transition volume fraction, which is typically around 60% or a little bit less. But then the interest has shifted somehow to soft colloids. And soft colloids, as I will show, actually comprise many different systems, like microgels, charged particles, star polymers, et cetera, et cetera. So one may ask, well, why should I study soft colloid? And I think that Paddy has the answer. Actually, he wrote the answer in this paper with other distinguished scientists a few years ago. And one answer is that actually true hard spheres do not exist in reality. So if we care a little bit about reality, well, soft systems may be interesting to us. Yep.
If I may interrupt, that paper was to be known as the hard sphere myth. However,
okay.
the co-authors didn't like it.
Okay, so I will correct the title here in the original version. Okay, cool. So we move from the myth to reality, and there is several reasons why studying soft particles is interesting. There is actually new physics that emerge when studying soft colloids in a glassy state, and this concerns the spontaneous dynamics. And there was a very famous paper that, with a very catchy title, that made the point that by tuning the softness of these particles, one may tune the fragility of a system, going from a very fragile system for hard colloids, like the hard spheres that have been investigated, and to a more, quote, Arrhenius-like behavior and strong behavior caused by the charges that are present in some of these systems. But still, this is an interesting feature, that you can have this strong versus fragile behavior. Another interesting feature that is not well understood yet, and we have observed it, but other people also report it, is what happens at very high effective volume fraction. So this is relaxation time measured in light scattering experiments as a function of volume fraction normalized with respect to the glass transition volume fraction. Here, glass transition is what you get from a VFT fit of your data in the supercooled regime. It turns out that because the particles are soft and you can concentrate them further, they are squishy, you can compress them, you can deform them, you can access samples that have this very high volume fraction. And here we observe that the relaxation time stops following the steep increase that was observed in the supercooled regime, and one ends up in a very funny plateauish-like regime with a very long relaxation time. This in absolute units, it's typically 10 to the 4 to 10 to the 5th seconds for measuring motion on length scales of, let's say, 100 nanometers or less, but with very little, if any, systematic dependence on volume fraction. And this anomalous high volume fraction dynamics is specific really to these soft systems, not something that is seen for hard spheres. Other interesting physics emerges if you go beyond the spontaneous dynamics and you apply some sort of drive to your system, for example, a mechanical drive, because these soft particles can undergo rearrangements that are not possible for hard systems. For example, in this nice work, Cayman and Russia have investigated this T1-like rearrangements, the kind of nearest neighbor exchange that people have observed in foams, but now with soft colloidal particles. And you can study lots of things, how these events are correlated in space, how correlation lengths change and increase on approaching the fluid to solid transition, et cetera, et cetera. Another interesting feature of soft colloids is the fact that you have actually a wide range of particles from which you can pick your favorite system with variable degrees of softness. And in this review paper by Dimitri Vlasopoulos and Michel Cloître, they show here systems classified based on their softness, from the softer ones, like polymer chains, to stars, microgels, emulsions, and then hard spheres, where you can continuously increase the steepness of the interaction potential between these objects. For one particular class of these systems, these microgels, you can actually have another interesting, very interesting feature, which is the fact that you can work with systems that are thermosensitive. For example, these PNIPAM-based microgels. And here, the interesting feature is the fact that because when you change temperature, the affinity of the polymer chains with the solvent, which is typically water, changes. You can actually produce these microgel particles, and their size, for example, here in the range of 100-something nanometers, will depend on the solvent temperature. And you undergo this transition from a regime where the microgels are fully swollen to a regime where they tend to collapse. And this, from an experimental point of view, is very interesting because it allows you to change the volume fraction of a system simply by changing temperature, which is very unusual for a colloidal system. And of course, changing temperature is much simpler than preparing a new system with a different number of particles inside. And you can also play games such as impose different temperature protocols to mimic what people typically do with molecular glass formers. There are also several open questions in the field. One is this question of fragility and the role of osmotic deswelling. The problem is that people have often tried to investigate what's the effect of softness of this system by changing the chemical composition, and changing the chemical composition often meant introducing different amounts of charges in the system. And it has been shown that these charges induce an osmotic deswelling of the microgels when you increase the number density, such that at the end you are mixing different things because you change the effective volume fraction, but you change also the effective interaction potential between these objects. So it's not very easy to figure out exactly what's what is zeta? Zeta is the effective volume fraction normalized by the effective volume fraction of the glass transition. And I will come, I think, in a slide or two to what this effective volume fraction is, because it's the typical quantity that people use in this kind of works. So this is one question. Can we make very soft microgels without introducing charges in the system and check whether the system is still fragile or becomes strong? Another question concerns the very interesting fact that I just told you, you can tune volume fraction in the system by changing the temperature, okay? But you can also do the classical thing in colloid-based system, which is changing the volume fraction by changing the number density of the particles. So you can have the same volume fraction with two different systems with a different number density and a different temperature. And then one question is changing temperature, changing volume fraction by varying temperature the same thing as changing volume fraction by changing number density? And there is actually one answer on the macroscopic length scale. This is work done in the group of Véronique Trappé, who showed that the macroscopic viscosity indeed can be scaled on a same master curve when you study systems where you have changed either the number density of the particles or the effective volume fraction by swelling and deswelling the particles at a given number density. But at a more microscopic level, as far as I know, there are no sets of data that show whether these two approaches are equivalent. This is PNIPAM, yes. Okay. There is the question of this funny plateau-like regime up here. So one possibility could be that these soft systems undergo a reentrant glass transition, which has been observed numerically by Ludovic and other people for soft systems, where basically if you increase concentration at a fixed temperature, you go from a fluid state, you enter a glassy state, but then you go back to a fluid state at very high concentration. So is this thing up there somehow related to this scenario or not? This is not clear yet.
Why do you have re-entries that, why do you have a fluid state at high concentration?
Okay, I think this is an excellent question for Ludovic at the next coffee break. My poor man understanding of this is that if you have a very compressed system, you are always paying a high cost in terms of elastic energy. So it doesn't really, I mean, you gain a lot in entropy if you introduce additional degrees of freedom by moving around things without paying a high energy cost, because anyways you have already compressed a lot your system. But Ludovic will explain that much better than I do.
Look at that they are changing their shapes, like instead of sphere versus ellipsoid.
Yeah, microgel that could happen.
Okay, this is simulated stuff.
Okay. But you see that in experiments?
I see that,
I think
which is different, but maybe not so different. And who knows?
No, but so, Luca, just to clarify, these are the model systems being considered are ones that don't have hardcore, they don't have a repulsion, right? I mean, these are soft spheres, as in particles can sit on top of each other and have finite energy.
They are Hertzian spheres. So you have this,
Yeah.
you do have a
the fact
repulsive
that
potential.
it's not, the core repulsion is not there is key to this behavior.
To overlap them, but you can overlap them to some extent. Yes, I don't know. I mean, if I had the answer, I would tell you the answer, but I don't know. It looks like it might be related. These two things might be related, but it's not clear yet. Yes. Yes, but at the same time, I mean, up here, if it would have followed the trend of the VFT thing, it would be like 15 orders of magnitude longer the relaxation time. So it's not going down, but it's not going up as it should be. Okay, and then there is really not so many works that address the question of the nature of the dynamics in these different regimes, and in particular works that have probed what is the length scale dependence of these dynamics. There is one such work by the group of Valentina Nigro and her collaborators in Rome. What they find is basically they measured the relaxation time as a function of scattering vector in scattering experiments. They find that for a given number density or concentration, there is a well-defined power law behavior of the relaxation time as a function of Q vector, but with different exponents. And they have some sort of semi-quantitative arguments to relate this exponent observed in the Q dependence of the relaxation time to the stretching exponent observed in the decay of the correlation functions, assuming that there is non-Fickian diffusion. But okay, this is the only thing which is out there as far as I know. So this is why we want to investigate a bit these systems. And we have worked in the past on regular NIPAM microgels. They are produced from NIPAM monomers to which you add a cross-linker and you polymerize everything, and you end up with something which looks like that, where you have a fairly high cross-linking density and a non-uniform distribution of the polymer of the monomers as a function of distance from the center. It's basically denser in the center and more fluffy at the periphery. In the group of Andrea Scotti, they synthesized these nice ultra-low cross-linked microgels. These are made without an additional molecule that acts as cross-linkers. Just during polymerization, there is a little chance that two chains that form will actually form a covalent bond between them. And the advantage is that you can get very soft particles because you have a very low likelihood of forming these cross links, and a very uniform particles. So they are ultra soft, they are homogeneous, they are not charged in the sense that, unlike other microgel systems, you do not add charge groups in the system. From a viewpoint of somebody who's doing light scattering, they are very convenient because they are very, the concentration is very low, so the scattering is just exactly what you need, not too much, not too little, so no multiple scattering. This is the typical size, 140 nanometers we work with, and the bulk modulus is about 1 kilopascal, and this is roughly 10 times smaller than what you would get for a regular microgel. Yes?
Yeah, so how does one measure the density of the gel from the center out?
Neutron scattering and then fitting, et cetera, et cetera, et cetera. Okay, so in the rest of my talk, we will be controlling volume fraction either by changing the mass concentration or number density or temperature.
Yeah, sorry, just a small question.
Yep.
What's the Poisson ratio of these things? Are they nice or are they auxetic?
Ooh, I don't know.
It's really nice. You're getting into the range where you get cells in stiffness.
Okay, just one word about effective volume fraction. It's basically you measure, you measure, for example, the viscosity of a suspension in the dilute limit at different concentrations, and then you map the observed viscosity as a function of mass concentration, which is the thing that you can measure experimentally, to the Einstein-Batchelor's form, and you extract from that an effective volume fraction. So basically, the volume fraction, which I will quote in the following, is the same as the hard sphere-like volume fraction for very dilute systems, but then, of course, you can concentrate this system because you can compress the particles. The way we studied light scattering, so light scattering measures an intensity correlation function G2 minus 1, which is the square of the intermediate scattering function. We use a commercial apparatus for fast dynamics and methods that I don't want to go into the detail, but they are specifically designed for very slow dynamics and non-ergodic systems that are based on this multi-speckle technique. And we have done the experiments both in the lab and on the space station, because like 20 plus years ago, we got accepted a proposal. And then it took like 20 years to actually do the experiments on the space station. And of course, during these 20 years, we have evolved. At the beginning, we should have been hard spheres, but then for a variety of reasons, it turned out to be microgels. This is the kind of intensity correlation functions that you measure. This is a system for a fixed number concentration, measured at different temperatures. And as you go down in temperature, the microgels as well, so the effective volume fraction increases and the dynamics become very slow. And as you can see here, this is 10 to the 5th second, so it's about 1 day. Dynamics can be really very, very slow. And the 3 sets of data are measured at 3 different wave vectors. The final decay of this correlation function can be fitted by this KWW function with a stretching exponent beta and a relaxation time tau alpha. So this is the relaxation time normalized by the relaxation time at infinite dilution. We have worked on various batches. In principle, it's the same synthesis, but each batch comes with a teeny tiny difference. So we observe the same steep increase and the same plateau-like regime that we have observed previously for regular microgels. One interesting observation is that, okay, this is the kind of fitting that we do for our data. We have these 2 batches. We get exactly the same kind of fitting with the same parameters, except for this 5G, which is slightly different. So indeed, we can compare things for different batches. And what I'm showing here for the ULC1 batch are both data collected by changing the effective volume fraction playing around with temperature, and data collected by changing at fixed temperature the number density. And they fall on the same curve, and this can be seen better here, where we have replotted things in reduced variables such that this VFT low shows up as a straight line. And you see that varying both number density or temperature gives the same result. So we indeed find that you can change volume fraction in different ways, and also at a microscopic level, not only for what concerns viscosity, you get exactly the same result. So this was one finding. Next, we looked at the structure of these systems using X-ray, small angle X-ray scattering. You typically observe a peak, which is sort of expected for these very dense systems. And here, again, we have played with 2 different ways of tuning volume fraction, either changing temperature or changing number density. So if you change temperature, the peak position is always at the same time, but the peak, this is better seen here, the peak becomes less pronounced when you go at higher effective volume fraction. So in this respect, you have something which, again, is a little bit reminiscent of this melting of the glassy phase when you increase volume fraction. Yes. I increase volume fraction, the height of the peak goes down. If I vary volume fraction, varying the number density, the peak position shifts, but also I have the same effect that the height of the peak goes down at higher volume fractions. This is sort of recap here. When you vary volume fraction by varying the number density, the peak position scales with a concentration to 1/3. This is just what is expected for a denser system. And you have this decrease of a peak height going more glassy. So if we put together this thing here with the observation, I start later, with the observation that, okay, thanks. Otherwise, I cannot get to the title of my talk. Okay, if you put that together with observation that you have the same dynamics, you have this sort of funny situation, at least to me, where you have systems that have the same volume fraction, different structure, but the same dynamics, which is, I think, quite unusual. So, in the interest of time, I will skip the plateauish thing, but I will be happy to answer questions about that and switch to the Q-dependence of the dynamics. These are my correlation functions measured for a system which is above this glass transition state at the beginning of a plateauish regime for different Q vectors. And this is the behavior of the relaxation time as a function of Q vector for a variety of different temperatures and hence volume fractions. So you have clearly very different regimes according to what the concentration is and what the Q vector is. You can have a very smooth and not so important decrease of a relaxation time with Q for a glassy system and a much steeper decrease for systems that are lower volume fraction. Now we play around a little bit with these data, and it turns out that you can overlap them onto a single master curve by rescaling each set of data with an appropriate relaxation time and an appropriate scattering vector Q star. And the interesting thing is that you can also take the data from the other group, the Rome group, where you had different behaviors at different volume fraction and put them on the same master curve. Here, what is shown here is the scaling factor Q star that allows to do this scaling. It is basically of the order of a particle size, 1/Q star, for diluted, for supercooled system, and becomes larger for more concentrated systems, implying that basically when you have a very concentrated system, you get the same behavior as a more diluted one, but on a smaller, more restrained length scale. You can fit this master curve, and this is the line, with various forms. And what we thought was a more physically sensible way of fitting it was to assume that the relaxation time is the inverse of a relaxation rate, and this relaxation rate accounts for two distinct dynamical processes, one dominating at low Q vector and one dominating at larger Q vector compared to this Q star. And depending on the volume fraction of your system, experimentally you explore more this part of the curve or the kink or the high Q part. Based on this idea, you can fit your correlation functions with not one single KYY function, but the product of two such functions. You get two modes, and basically you have the mode associated to the behavior at low Q, which exhibit a very small Q dependence, a compressed beta factor. And this is something that has been reported for other jump systems. So we think that this is associated to this story of relaxing internal stresses. And the mode that prevails at high Q vectors has a very steep Q dependence, typically Q to the minus 4, Q to the minus 5, and has a stretched exponential shape. And we think that this is associated to some very local motion of the polymer chains within the microgel. So we think that this is specific of these microgels. And we don't have a direct proof for that, but interestingly, there are out there some other data. People have studied silica particles with hairy NIPAM chains in an experiment where basically you only see the silica particles. And in that case, they don't, I mean, their data cannot be put on this scaling stuff. Okay, this will be really my last slide. So, on-ground data, this is our relaxation time that increases very steeply with volume fraction. Then we took the same sample on the space station, it does that. So we don't understand anything. Of course, we'll never get the chance to do the same experiment twice in space, but we will get a chance to get the same sample exactly in the same machine, loaded in the cell with the same procedure, because one can think of many things that could go weird, and try to understand why we have this very big difference. And with that, I will end here. Oops, this is not what is supposed to be here, but anyways. So thank you very much for your attention.
Okay, so we can have a few questions. Patty, Mark, and Ranjani. We need some theorists asking questions as well.
The last thing you just very briefly, I'll pester you more at lunch, but the microgravity, what's the gravitational length of the particles?
It's very small because they are made of water, essentially.
You mean it's very big?
Oh, yeah, it's
the
very
gravitational
big.
length
Sorry,
is
yes.
very
The
big.
effect of
The
gravity
effect of gravity
is
is
very
tiny.
small. So
Yeah.
I would not have expected any effect of gravity, actually. So this is very surprising. So that's why I put my preliminary stuff there.
When you say it's very, what is the gravitational length? Like 100 diameters? A
I
millimeter?
honestly, I didn't calculate it, but it's like a particle of 150 nanometers made 95% of water, and the rest of a polymer which has a mass density which is not huge. So it must be really super big. I mean, you can centrifuge these samples, but it takes time. So that gives you some idea.
Okay, Mark.
I have page 17, slide 17, I have a question about the experiment. So in panel A, I noticed...
I'm sorry, this is on ground, this specific thing. Okay.
Got it, great. So in panel A, I noticed that there's this tendency for the data at long times to drift down a little bit, way at the bottom. And the fit, of course, does not show that. Is that a real feature of the system, or is that an experimental artifact?
I think that, so, I would tend to think that for a very diluted sample, this is quite minor, and I don't trust it. For more concentrated samples, this has to do probably a little bit with the dynamics not being completely stationary. So they tend very slowly. I mean, we try to average the data over different time windows. The overall shape does not change significantly, but you have some slowish thing growing with time, and that probably is related to that.
The baseline is also not the same in each panel, right? It's,
Well, wave, no, this is, well, it's written up there. But this tendency is there, that's true.
So, Anjali, last question.
Yeah. So, two things. I have to ask something about the microgravity experiments. So, you didn't show us the betas there, the beta values. You just showed the relaxation time.
Right.
So, I was just wondering what kind of values those take.
Honestly, I don't have it in mind because it's really very, very preliminary. For the experiment on ground, you have this this non-monotonic behavior of beta that
Right.
goes down on approaching the glass transition, then goes up again. And I think that this, you don't have it in the microgravity data where everything goes smoothly. So you would be in something like around here, but we need to check.
Okay. And in these experiments, you never quite, oh, you do reach 1.5, the
Yes.
beta of 1.5. And
Yes.
okay. Okay. The other quick question is that what is the relaxation process that gives rise to tau alpha going as 1 over q to the 4 last?
Good question. So I have asked many distinct people and scientists, and nobody could really explain me that. So you can just cook up an argument, say it's a very, it's a very steep kind of motion. It's not ZIM, it's not Rouse. There were some very old MCT calculations of, but this is a melt of short polymer chains which would have a regime where you observe Q to the -4, but I'm not 100% sure that that is relevant to what is seen here. So it's some sort of very localized chain motion, we think, but we don't fully understand why Q to the -5 or Q to the -4.
Okay, two last questions, short questions, quick answers. Somebody
Thanks,
else?
Luca, for the nice talk. So, to mimic the, molecular glass transition, we are trying from soft colloidal glass to, hard colloidal glass. So my question is that, according to our current understanding, what are the, difficulty we are facing to make one-to-one analogy between this, colloidal system and this atom?
These colloidal systems and?
An atom, molecule.
And molecular glass formers. Ooh.
Good
No,
question.
I think, you can map some features like the VFT increase, et cetera, but then there are other features that I think that are really specific to the microgel structure, et cetera. These were the
Okay.
short answers.
Last question.
Just a quick question. So in the previous slide, you showed the temperatures 29.75, 29.5, etc. So how do you exactly measure this temperature? How do you ensure the uniformity? And
That's the,
Yeah. So this setup has been built by a Belgian company, which is very poor in doing everything related to scattering, but excellent in doing temperature control. So they have this cell which is enclosed in a big copper unit. They have 3 thermocouples that measure temperature at different spots in contact with a cell, and the temperature gradients and
Misaki
temperature
setup.
stability is really very, very good.
okay, I'd like to know this because we're trying to get some uniform temperature distributions in some setup, and it was very, very difficult. So what would be the standard deviation here?
The
Like when
center-
you have 29.75, it would be, what would be the standard deviation?
I'm sorry. The other standard deviation?
Yeah, standard deviation of the
It's
temperature.
like a few millikelvins or something like that. It's really small.
Thank you.
Sure.
okay, let's thank Luca.
Thank you.
Okay, so the last speaker before lunch is Misaki Ozawa, whose title I don't have.
I think this.
Okay, predicting dynamics of glass forming liquids with
Oh, yes.
interpretable machine learning approaches. So
Okay, hello.
I'll alert you when you have 2-3 minutes to go. So don't. I'll alert you when you have 2-3 minutes to go, plus questions.
Okay. Hello, everyone. My name is Misaki Ozawa. First of all, thank you very much for organizing this nice conference. Today, I'd like to talk about prediction of grassy dynamics using machine learning, but more focusing on interpretability, physics understanding. Okay. This work is in collaboration with Daniel Kosrovich, Chen Liu, and Anand Sharma. He's a great Indian internship student. Okay. Since I heard that half of the audience is students, so I spend a bit of time for pedagogical introduction. So this work is concerning about structure and dynamics relationship. Many people from all over the world, particularly in this audience, people have been trying to understand the mechanism of dynamical heterogeneity in view of local structure, local structural environment. People have been trying to identify relevant local structure responsible for future dynamical heterogeneity dynamics. This line of research is recently boosted by machine learning technique. In short, starting with the data set composed of structure, configuration of particle, and the corresponding future dynamics, mobility data, a bunch of machine learning techniques can identify, find the relationship between structure and dynamics. So once machine learns this relationship, machine can predict future dynamics of grassy material just looking at configuration. Okay, so this figure is taken from a very recent nice review paper that I will come back later. Okay. So typically, so one of the most useful quantity to look at in terms of dynamics is propensity of motion. The starting with a given configuration, we perform molecular simulations many times with different initial velocity, different initial random number following Maxwell-Boltzmann distribution. Then we measure displacement averaging over many trajectories. So this is the propensity. On the left-hand side, I show the ground truth, meaning that this is simulation result, okay, of a propensity map P. You can see a dynamical heterogeneity. The red region corresponds to the mobile region, and the blue region corresponds to the immobile region. On the other hand, since this is now still in introductions, I do not specify the specific method of machine learning, but this is machine learning prediction of propensity, p hat. Okay, so you can see that machine learning can predict more or less the heterogeneous pattern of dynamics by just looking at a snapshot. Okay, and how to evaluate the performance of machine learning prediction? So people often use Pearson correlation coefficient, law between ground truth propensity and prediction p hat. Okay, so if you have a perfect prediction, you have a linear straight line. Machine learning prediction is not perfect, but you see some scatter plot following a straight line. And this, in this example, the Pearson correlation coefficient is 0.77, which is quite good. Okay. In terms of enhancing the performance, the Pearson correlation coefficient of prediction grassy dynamics, people from all over the world trying to sort of compete. They are competing in terms of prediction. So in this nice summary plot from this review paper by Giulio Ludovic and and the quarkers, you can see basically two classes of prediction. The bottom parts are sort of human-designed, the conventional descriptor or structural feature such as local energy, bond orientational order, something physically interpretable and designed by a human researcher. Okay. On the other hand, on the top part, you see a bunch of techniques based on machine learning, such as neural network, support vector machine, etc., etc., etc. So you can see that the machine learning approach is much better than human design prediction descriptors. Okay. Okay. So although machine learning prediction is very good, and as it is very well summarized in the previous review paper, but still there is a problem, which is interpretability and understanding. Because typically, machine learning method is considered as a black box. So we don't know what's going on inside, in particular, deep neural network. Therefore, high performance, high accuracy of prediction does not mean we understand something, the mechanism or physics interpretability, etc. So actually, this issue is also very important hot topic in the machine learning community itself. As you can see, interesting paper whose title is "Predicting with Not Understanding." Okay. So when I started to work on machine learning, my friends, my colleague criticized me. Machine learning is black box. So as a physics research, what do you learn? You don't understand physics mechanism, so why you use machine learning? So my first answer is because it is easier to get a job. It is easier to get a grant, okay? But my second answer is because, so this is precisely what we need to study, okay? We need to shift from increasing accuracy to more understanding, getting physical insight from machine learning. So this, my talk is along this direction. Okay. In terms of interpretability, so there's a trade-off between interpretability and accuracy. So this plot is taken from the internet. The y-axis is interpretability, and the x-axis is accuracy. So linear, simple model like a linear regression has a higher interpretability, while the accuracy is small. On the other hand, deep neural network has a very good accuracy of prediction performance, but interpretability is very low because of black box. Okay. Ideally, people, we wish to have something very interpretable at the same time, very, very accurate. That is the ultimate goal. Okay. Along this line of study, there's a very nice stream of, very nice story initiated by Google DeepMind using cutting-edge neural network, graph neural network at that time, 2020. So they performed unprecedented accuracy of prediction of glassy dynamics by just looking at a snapshot and configuration. After that, the group of Laura Filion, they thought about what is the mechanism behind this unprecedented performance of DeepMind graph neural network, deep learning. And they thought that they identified that the sort of the coarse graining of local structural feature is the sort of essence inside this graph neural network. And once they identify this essence, the group of Filion developed a simple linear model plus coarse-grained features, feature mean some local structural quantity, and the prediction becomes almost same as the graph neural network of DeepMind. That is a very remarkable study, and in our work, we want to go further along this line and try to understand it and try to get physics understanding from the machine learning result. Okay. So this is our, we perform computer simulation. So this is our simulation model. We study a two-dimensional ternary Renard-Jones mixture. And we perform Monte Carlo Brownian-like dynamics at a structural relaxation time scale. And we computed mobility or propensity using isoconfigurational ensemble. And we measure local or structural quantity, structural feature at the inherent structure of configuration. Okay. And in order to quantify local environment, local structure, we consider three different types of descriptor. So here a bit of language. So when I say descriptor, so descriptor means a set of structural features. So this is a bit like a machine learning terminology, but this descriptor vector has M component, M features, okay? The first one, let's say descriptor A, is widely studied, used by the group of pioneering work by Andrea Liu. So they consider radial component features and angular component features, and they vary parameter inside systematically, and they have 276 features. Okay. Again, the idea is to try to expand the structure space as much as possible. Then descriptor B, let's say, is studied by Gerhard Jung and Giulio and Ludovic. They consider more physics-informed style, local energy, local density, perimeter of a Voronoi cell, and they consider sort of information about species A, B, etc. Besides, they perform constraining of feature systematically from short range 0.5 up to 5.0. And then they have 120 features. We also consider a descriptor C. In our setup, we take into account Tanaka's order parameter characterizing local efficiency of packing, local energy, local number density, bond orientational order psi 6, local packing fraction, coordination number. Besides, we perform also coarse graining, and we have in total 60 features. Okay, so how to do linear regression? First, we make a model for propensity prediction P hat for each particle I. So P hat is expanded by linear combination of these features with associated weight, W, okay? And we can show a vector form like this. W and X belong to M-dimensional vector, okay? Since this is a machine learning, we wish to minimize sort of loss function, in our case, mean square error between prediction Pi hat and the ground truth Pi, okay? And we perform derivative of L with respect to the vector W. Okay? This gives you the solution of this linear regression, which turn into the inverse matrix of correlation matrix of feature, like this, times the Pearson correlation coefficient of feature and propensity. Okay, so this is standard linear regression approach. Okay. Usually in the literature, we make people say, "Oh, we made a linear model," then just happy. Okay, but we need to think about why linear model is interpretable, and we can get some insight. So here in this slide, I just record this. Why linear model is interpretable? Because the weight in front of feature carries some information about each feature. For example, when W is positive, when X increases, propensity increases. So it means that this feature contributes to propensity becomes higher. So it's more mobile. Okay. On the other hand, when the weight is negative, then when the feature increases, propensities go down. So it means that this feature have some effect of slowing down dynamics. Okay.
The features are like this local order parameter or something,
Yeah.
like Tanaka order parameter.
Yeah, you can.
But then you
think
only
about
listed
whatever.
some of them, and you are using 60 of them.
Yeah.
So what are those other?
For example, Andrea Liu group studied radial component. Looks like a local radial distribution of functions, sort of angular among three particles, among neighbor particles, or local. Oh, okay. So I have a 6 order parameter, theta, local energy, local number density, psi 6, local packing efficiency, coordination number 6. And for each order parameter, I perform coarse graining from 0.5 up to 5, 10 times. Okay. So a priori, we don't know what is the best coarse graining length. Machine should decide. Okay. Okay. So this is the idea.
Misaki, one clarification. So these descriptors themselves don't have any overlaps. Meaning there's two in which there's a local number density or a local density.
Yeah.
So when you now say one model is better than the other, what's the extra information that went in because the descriptors don't have overlaps?
So very good point. Actually, there's overlap. That's the key point in my talk. Okay. So you will understand this. Okay. Okay, okay. So, and I said the sign of W is important. Of course, the magnitude of W is important. It means if you have a very large W, it means that this feature is very important. Okay, so not exactly, but this means that this is kind of a phenomenological constitutive equation connecting different quantity and dynamics. Okay. This looks good. However, there's a very big problem. If you look at the W's and trying to extract some physics information, actually it's quite a mess. So the W fluctuate and oscillate like this. I showed this example. So the error bar corresponds to the data set to data set fluctuation. We confirm this kind of messy behavior for all descriptor we considered. So the problem is, while the prediction accuracy is high, as I said, and also Laura Filion's group demonstrated, and also we have a very good generalization, no overfitting. However, there's a huge data set to data set fluctuation in terms of weight. So data set to data set fluctuation means that although the data are extracted from the same physics condition, potentially the same distribution, but each time W fluctuate. Okay. This can be, in principle, suppressed by using very large data set, a very large number of data points. However, after removing this fluctuation, we still have a strong oscillation of weight among physically similar features. So this is counterintuitive, or it's not good, because physically similar features should have the same sign of W and also similar magnitude. Instead, they are oscillating. So we cannot extract the physical interpretation at all. Okay. So the reason, the mechanism behind, well, but the mechanism behind is precisely what Raja expected. It's due to so-called multicollinearity. Because some features in high-dimensional, m-dimensional features, some of them are highly correlated. On the left, I show the correlation matrix here for different features with different coarse graining length scale. You see that some part, there's a huge correlation near red, near anti-correlation near blue. Okay.
Rajesh, you were talking about the different descriptor sets. Yeah, slightly different than what he had in mind, but
Oh. We will come back later. Okay. Okay. Okay, so symptom, well, mathematically symptom of this multicollinearity appear as a minimum eigenvalue becomes 0. So the matrix become singular. Okay, then if you look at the textbook, statistics textbook, we can mathematically explain the divergence of fluctuation of weight, W. So by using eigenvalue decomposition, we can show that the variance of W can be written by the inverse of eigenvalues. Okay? So obviously, when you have a vanishing 5 minutes? 5 minutes? Okay. Vanishing eigenvalue, so this variance diverges. In terms of strong oscillation, so this is, as far as we know, this is not discussed well in the statistics community. Nevertheless, we can still understand that this W oscillate when eigenvalue is vanishing. In particular, the correlation matrix has tapered-like block matrix, as you can see here. So these are looks like a tapered, so-called tapered matrix. Anyway, these are some mathematical expression, but they cannot tell us how to overcome the situation in practice. In statistics textbook, a couple of methods or remedies for multicollinearity are proposed. The first one is put regularization, in particular ridge regularization, put additional penalty term with some magnitude alpha, with W squared. This is good, and indeed, the multicollinearity is suppressed. However, the shape of W, weights, changes significantly when alpha is varied, while the prediction accuracy is almost same. So therefore, we don't know which value of alpha we should use for physics interpretation. So far, we don't have an optimal alpha to extract the physics interpretation. Another method is principal component analysis using diagonalization, linear transformation from original feature to new feature. So this is very good to discuss, well, in particular, removing the modes associated with the small eigenvalue. However, after transformation, the original features are mixed somehow, and it's hard to interpret. Okay. So the last option here is the feature selection. The problem is that, so we start with so many features from the start. So why not select only relevant, important features while keeping the prediction of dynamics? Okay, so feature selection. So we try several feature selection methods. The first one is so-called lasso selection. Again, we put the penalty term, but with the modulus like this. We don't put square here. And because of this penalty term, some features, irrelevant features, go away. So the weight becomes 0. After that, this last selection find 5 good features. The Tanaka parameter at the coarse grain length 2. Tanaka parameter coarse grain 2.5. And local energy 1.5. Local number density at 0.5. And local packing fraction at coarse grain length at 1.0. And with good prediction accuracy. This is the last selection, assuming the linear model, so it means that it's suitable for linear regression. We also try another feature selection method. So I do not have time to discuss in detail, but this method recently developed by a group of Sissa in Italy. So they do not assume particular type of model, like a linear model, but we get different set of features, okay? Or maybe some feature like a Tanaka parameter at coarse grain length 2 and the volume fraction, local volume fraction at the coarse grain length 1 would be a 2 key feature. But in general, what we observe, what we get, depends on the feature selection algorithm, although the performance is more or less same. So this concludes that, okay, we get some good hint, but still, even a linear model, it's hard to extract precisely the physics intuition starting with machine learning method. Okay, so I have 1 minute. Okay, so I just briefly say, so in this talk, for the moment, I discussed the mainly linear model, but we also try to start with deep learning, and we try to make a path toward higher interpretability, okay? To this end, we take the best machine learning architecture shown in this review paper, SE3, developed by the group of Francois Lanz. So this neural network is very good because it satisfies rotational and translational symmetry in a material. So in order to preserve this kind of symmetry, so neural network operation contains convolutional kernels satisfying translational symmetry, and spherical harmonics are used to treat rotational symmetry. Anyway, still there's some black box inside here. So we have a patient to look at all these functions and carefully check each layer in a deep neural network. For the moment, we find that for each layer, so the machine takes into account only short-range interaction, but with taking into account more layer, deep layer, machine takes into account longer range interaction in a layer-by-layer manner. Okay. Besides, we try to develop more interpretable neural network method using the so-called transformer, which is a sort of golden standard in machine learning. In our context, the transformer learns the relative importance between two particles in a system. So we machine learn this sort of weight, Wij. Based on Wij, the feature, now feature is written as H, okay? Feature of particle I is updated or transformed by taking into account the neighbors. Okay. So this is still a preliminary result. And one good news is that so we get great improvement in terms of short time prediction compared with Francois Lanz's symmetry preserving neural network. But still, we have a significant overfitting at the longer time scale. And we need to make a lot of effort to reduce overfitting by tuning hyperparameter, etc. Okay, so let me conclude. So the first part, we try to extract some physics meaning, physical interpretation, starting with machine learning, in particular linear model. We haven't concluded yet, but our message is even a linear model, it's still hard to extract some good physical intuition. On the second part of my talk, so I try to start with neural network and try to increase the interpretability of model. Thank you.
Thank you.
I wonder, and you didn't mention the system size dependence. Let's say if you increase the system size, do you need to increase the number of features, and do you lose on the predictability?
So usually people, in this kind of model, in particular the one that I showed, so we compute a feature, right? So the coarse grain length is from 0.5 up to 5. So it means that the machine takes into account the neighbor up to 5 in 2 dimensions. So if you have a sufficiently large system size, for example, 1,000, 4,000, we believe that the result does not change
you don't have a system size decline in the predictability?
So far, no. So far, no. Yeah.
Because the trajectories become very, you have a huge increase in the possible number of dynamical trajectories. So I'm a bit surprised that you don't see a predictability decrease.
So, but aside from machine learning, is there such huge dynamic finite size effect in the glass forming liquid? Not that much. I think if you have a 10,000 particles, I think people confirm that at least within temperature range we can access, more or less system size dependence is converging.
Okay. Peter.
Okay, I had one quick comment and one question. I mean, the comment was, obviously, if you have a very redundant feature set like you have, or collinear as you call it, then it's not surprising that the answers you'll get in terms of which features are most important will be hard to kind of pin down, right? Because you can more or less exchange features, right? Exactly. So there are other methods, like, for example, feature aggregation, where you basically try and group features to reduce collinearity. That might help with that, right? The other thing that I was curious about, have you tried Bayesian methods? I mean, for example, these problems of how to select the optimal ridge regressor, they have reasonably principled answers within Bayesian settings.
Okay, so for the first question, I'm happy if you find such kind of method, automatically find a good pitch. But what I can say is that in terms of deep learning method, so we don't prepare features from the beginning. Okay, so we just feed only configuration and the position coordinate, and the machine deep learning automatically find the good feature. But then, but this is one way to extract the feature automatically. But then interpretation is confusing, and then it's hard to say, or this feature and correlated with this feature, because all the information are mixed up. The second one, yes, the Bayesian approach, we haven't tried, but the Bayesian approach gives us some good interval of a good hyperparameter, blah, blah, blah. So, but I think it's an idea, but so you are saying that within some interval predicted by Bayesian approach is a good candidate for physics interpretation.
Yeah, I mean, there are Bayesian-based methods, for example, for choosing an optimal ridge regression alpha parameter that you had, where you basically you just choose them, you maximize the marginal likelihood of the data sets that you've got, right? Or similarly, as feature selection algorithms, right, you can use Bayesian priors which you then tune to get the best likelihood, and that is a feature selection method. So that might be useful as an alternative to look at.
Okay, thank you.
Okay, so Giulio, then Indrajit, and Sarika.
So I was wondering if you tried something very simple, like, so you have a big fluctuation of the W if you change the data set. But what you could do is you could just average them over the data set and then see whether the prediction is more or less the same once you average them, in the sense that you could think that you have big fluctuation in the weights, but they are irrelevant for the prediction. So if you average out, maybe you get something which is interpretable.
Exactly. Very good question. So we also, instead, not only looking at data set to data set fluctuation, but also we average over all, we use all entire data set, then we can suppress the fluctuation considerably. Okay, so this part in principle, is same. However, the main point is that still oscillation part remains. So we have a two issue, fluctuation, data set to data set fluctuation, and oscillation. Actually, they are two different phenomena. And even if you have a perfect statistics, but still oscillation of weight remain.
Yeah, nice work. So you have around 6 feature space, right? So among those, you find that Tanaka's order parameter and some of those like local energy, they give kind of a very similar informations on the propensity, like p-hop. Okay. So if you just kind of, this is kind of a telling that they're almost carrying that similar kind of information. So if you just try to rule out one of these things, for example, only use those Tanaka's order parameters, so how much information you are going to lose? So I'm just thinking how they are correlated in terms of their.
Okay, so in terms, okay, you are saying that starting with a full set, then remove one feature and then check how much performance decreases. This gives you some magnitude.
Exactly.
Yeah, this is a very good naive idea, but actually it's not straightforward. Why this Tanaka, for example, Tanaka parameter may be good if other parameter exists.
Yeah, so this is, are you gaining something so to put all these 6 things? For example, if you have only these Tanaka's things and over it you just put the local energy.
If just Tanaka order parameter we use, this corresponds to nothing but just a Pearson correlation coefficient between propensity and this Tanaka parameter, which is about 0.55 or 0.6 or something like that.
And the fluctuations, because you see a very large fluctuation on the particle level, right? That
fluctuation?
The fluctuation, for example, that each particle describe those dynamics, right? So for example, if you have this Tanaka structural order, how they are correlated with kind of a propensity. Okay, you see this, every particle is not kind of a one-to-one correlated. There is a large fluctuation.
Yeah, there's a particle fluctuation.
Yeah, so is it kind of a larger or smaller? Did you measure those fluctuation on the different structural?
So maybe some of it, make a quick answer, but you should follow it up later. Yeah.
So actually, I'm not sure what is the question. We can discuss.
Yeah, because the lunch break is tight. So
yeah. No, my question was also a little connected to what he's trying to say. So do you understand any correlation between the order parameters from your study? You know, how Tanaka's order parameter will be helped by the density at like L1, and like, is there a way to find out the correlation between the order parameters also in that way?
Yeah,
like how one would help the other in better
so far,
prediction?
what we showed is that just a correlation between 2 features.
Right.
But okay, so correlation among feature.
Yes.
I think the machine learning community has a method called the SHAP analysis. So for example, so you have 3 features, and when feature A and B is absent, what is the performance of C? And when the A is present and the C is absent, what is the performance B? So there's a combinatorial way to check this kind of importance. Yeah, but we haven't tried it yet.
Okay, so let's thank Misaki. We should break for lunch, and before that, do you have anything to?
How can I say anything?
No. So, yeah.
So there is something. So there is always something. So all the schedule has been emailed to all of you. Okay, if you haven't got it, we'll email it to you. And also the settings have been changed. So even with this Wi-Fi address, you should be able to download the schedule. But this we haven't checked. So.